Okay, so it is live now.
Okay, thank you. So good afternoon, everyone, and I welcome you all in this lecture. And today's speaker is Professor Lee William Packer. He is from United Kingdom Atomic Energy Authority, and he is also affiliated with International Atomic Energy Agency. He is here to give IPA, IoP, Cockcroft, Walton lecture series, and this lecture has been scheduled at 3 places. First lecture was on in BARC, our Atomic Research Center. Second one was at IPR, Institute for Plasma Research. And third one, and the third and last is here at IUAC. So in the morning, he had visit to different IUAC facilities, and I'm sure that you might have enjoyed. So I will introduce the speaker. Professor Packer is an internationally recognized expert in nuclear science and technology with over 25 years of experience in research and industrial nuclear sector. He is a fellow of the Institute of Physics and UK Atomic Energy Authority fellow since 2023. Packer leads R&D themes in the development of nuclear fusion technology. His work in applied research spans critical areas such as neutronics, nuclear forensics, radiation detection technologies, and metrology, which are essential for advancing nuclear technology. He has contributed to international nuclear programs, including ITER, Fusion, IAEA, and NEA. With this small introduction, I invite Professor Packer to give lecture on perspectives and challenges within the development of nuclear fusion energy. Professor Packer, please.
Thank you very much. Yes, thank you, Dr. Kumar. It's a great pleasure for me to be here. This is my 5th day in India on this trip, and it's been such an amazing trip, and I'm very grateful for all of the organization that's needed to go into this trip. So far, I visited BARC in Mumbai, and I spent a couple of days there, hosted by Professor Kripamai Mahatta, and visited the Dhruva reactor and had very useful discussions. And it was fascinating. And then I visited IPA and talked to them about fusion and managed to see the excellent capabilities in plasma physics, but also in technology areas. I was really impressed with the Neutron facility, the Tritium breeding blanket capabilities, the metal coolant and solid breeder work there. So I was really taken away with that. And then coming here to UAC, it's been excellent this morning to see the accelerator capability you have here. Seeing the work you're doing on the Indian MRI scanner, and the AMR capability, the Tandetron, and so it's been fascinating, and I'm much more knowledgeable about what's happening in India in science and technology. So my lecture, Perspectives and Challenges within the Development of Fusion Energy. So as Dr. Kumar was saying, my background's in neutronics and radiometrics, and I will talk a bit more about this later. So a few acknowledgements of come this side, yes. Use this pointer.
Oh, you can change this slide.
Right, I can use this one. Yes, good. I've got the old-fashioned pointer here. So I'd like to thank the Institute of Physics, Miriam Dembo in particular, and Natanya, the Indian Physics Association. As you know, the Cockcroft, Walton, and Homi Bhabha lecture series. It's a bilateral exchange between India and the UK. So every 2 years, you have an exchange of scientists. And I believe we'll have an Indian physicist coming to the UK to talk about topics doing a kind of similar reciprocal tour. I'd like to thank these host organizations, BARC, IPR, there's Professor Pinto, Dr. Vala, many colleagues, and of course here, Dr. Kumar, and the many colleagues that I met this morning. I'm going to show you some material, and some of it's my own work, but of course I want to give you a kind of international perspective and a UK perspective. So I would like to acknowledge several others who have contributed to the material shown. And down the bottom here, I will share you some of my views. They're not necessarily the views of my organization, but we'll get started. So an overview of my talk. So I'll just give you a bit of an introduction to fusion. I realize many of you know a lot about fusion. I've met I had some really interesting discussions already in India around that. We'll go through what is the international landscape in fusion. Then I'll get into neutronics and its essential role in fusion design. Neutronics is essential to any nuclear technology that's producing energy, like fission, accelerator-driven systems, and of course fusion. Fusion being a neutron-rich energy source. So we'll go through methods, nuclear data, models. I'll go through some of the benchmark experiments and validation, and pick out a few highlights. And then at the end, I'll come back to a few of the recent developments within the UK. So I'm just going to start with a kind of a motivation slide, and I acknowledge my CEO, Ian Chapman. I've adapted a slide from him in this presentation here. So this you already know, the global primary energy consumption by source, and this data from the Energy Institute shows the energy consumption since the 1800s. Shall I use the laser pointer? Yeah, okay. And basically, globally, we've burnt about 50% more energy and more fossil fuels than we did back in 2000. And you see here the biomass, coal, oil, natural gas being the fossil fuels, with the nuclear, wind, solar, and so on in a much smaller proportion. So about 80%, slightly over 80%, made up of fossil fuels. You know, what does net zero mean? Well, it means displacing that contribution. And, you know, there are various targets for hitting net zero. And I think India's is 2070, I believe. And you'll bear with me with this back of envelope calculation. And it can be criticized, of course, but I just wanted to put this into context of what would be required in terms of displacing this. So there's about 15,000 days until 2070, actually around 16,000. Looking at this contribution here, this adds up to 150,000 terawatt hours per year. So we need to displace, you know, this, and this is about, you know, we need to build a capacity of 10 terawatt hours per year each day. So you divide one by the other, you get this 10 terawatt hours each day that we need to kind of displace. And that's neglecting any growth in demand. And you can see the trajectory, it's only going upwards very fast. And, you know, what does that mean, you know, displacing 10 terawatt hours per day? Well, one nuclear power station is around, broadly speaking, around 10 terawatt hours per year. So it's, you know, so, and what does a nuclear power station cost? Well, in pounds, it's around 10 billion, roughly. So, and if you add this up, it comes to about 4% of global GDP. So, and this is a huge, this is a you know, huge fraction of the GDP. And if you look at what we're actually spending on addressing this challenge, it's only a tiny fraction of that. So, hitting net zero is hard. It's going to be extremely hard. And to say that, you know, a lot more needs to be done to do that. Nuclear can play a role. I'm not going to argue here that fusion is going to help to hit that target, but it can help to provide us with a sustainable future moving ahead. So we're going to need solar, wind, nuclear to be able to hit these kind of targets. I will just sort of enter with a quote from the late Stephen Hawking, who in his last ever book, he was asked this question: what world-changing idea, small or big, would you like to see implemented by humanity? And he said, this is easy. I would like to see the development of fusion power to give an unlimited supply of clean energy. And I think you could do a lot worse than, taking advice than Stephen Hawking. So what are the benefits of fusion? The first here, fuel abundance. The fuel in fusion reactions are abundant. So I'm going to be talking mostly about deuterium-tritium fusion, and there are many possible fusion reactions, but this is the type of fusion that largely we're pursuing for terrestrial machines. So deuterium is readily extracted from seawater. I know India knows a lot about deuterium and in use of the D2O reactors that you have. And tritium is produced from lithium. And we have a lot of lithium. So there's an abundance. There are estimates 30 million years, but there's a long time, a large amount of supply there. So, and of course, like fission, base load power. So fusion could be deployed, in that way, and it doesn't depend on external factors such as wind or sun. Continuously deployable at the point of need. High fuel efficiency. Fusion produces more energy per gram of fuel than any other process that could be achieved on Earth. So fission is extremely energy dense, isn't it? And fusion is about 4 times as energy dense as fission, and about 10 million times the energy density of coal. So carbon free at the point of generation. One important distinction between fission and fusion. So fission depends on a chain reaction to keep the reaction going. Fusion is a thermal process. You heat up gas, ionized gas, to very high temperatures, and you need to keep it hot for fusion reactions to take place. So, and if you remove that heat, the reaction snuffs out. So if there are any technical problems with operating a fusion plant, the process would switch off. Radioactive waste. So fusion power plants will produce radioactive waste. They're not expected to produce the high-level radioactive wastes that are associated with fission. So that's a relative benefit. But it's hard. So temperatures inside fusion machines, tokamaks, for example, will be 10 times hotter than the center of the sun. So the center of the sun is something like 15 million Kelvin. And inside a tokamak, the temperatures are around 150 million degrees or even hotter. So how do we keep this plasma at those temperatures? Now, one route is to use a tokamak, a magnetic confinement approach. So the fusion fuel is suspended inside this magnetic cage. So the fusion fuel is suspended inside this magnetic cage. We keep the plasma hot in this way. And there are other approaches to fusion as well, which I'll come on to a little bit. Now, we talk about the DT reaction, and this is the reaction I'm talking about here. So deuterium and tritium, it undergoes a fusion reaction to produce an alpha particle, helium-4, plus a neutron. And you release 17.6 MeV in the process. And of course, this curve here, which you'll recognize, the binding energy per nucleon curve, can tell you how you can get energy out of either fission or fusion. Fission, you start up here, you undergo a fission reaction, produce 2 fission products. You can release energy in this way by the delta mass difference multiplied by c squared. And then fusion, you're fusing light isotopes into heavier isotopes and doing it this way. This back of envelope calculation down here just shows you that energy density comparison I made earlier. So DT fusion is a factor of around 10 million times the energy density of coal and 4 times the energy density of uranium. So how hard is it to achieve fusion? You know, and what do we mean by fusion? Well, what we need to do is to produce net energy. We need to get a net energy gain out of fusion. And there are three quantities that really matter when you're trying to achieve fusion. They're known as the triple product, which is closely related to the Lawson criterion. John Lawson was a scientist that worked in the UK at Harwell, and he produced a paper in the 1950s looking at this criteria. And the three things that matter are the plasma density. How dense is your plasma? What is the temperature of your plasma? It's the second factor. And third factor is energy confinement time, which is roughly analogous to if you put energy into your plasma, how long does it take to work its way back out again? And if the product of these three factors is greater than a certain number, and this number here, 3 times 10 to the 21 keV seconds per meter cubed, is this criteria. And it's quite interesting to look at this space. So if you plot energy confinement time along this x-axis and ion density on the y-axis, you can start to plot different facilities. And this is from this paper from Ian Chapman and Nick Walton. Tokamaks typically have high energy confinement time. They retain the energy in the plasma for a period of seconds. So JET, the Joint European Torus, which is the tokamak based at UKAEA at Cullen, is in this space here. ITER will have better confinement, so longer confinement times, and relatively low plasma density. And if you look at the other end of the spectrum, and you may have heard of inertial fusion. So there's a facility in the US called the National Ignition Facility, which is producing inertial fusion shots using energetic lasers, which impinge on a gold hole round, a gold cylinder, to create an X-ray bath, which collapses some fusion fuel in a capsule the size of a peppercorn, and the outer surface of this capsule ablates, creates extremely high densities. So you get very high densities, orders of magnitude higher than in a tokamak-based plasma, but the energy confinement time is on the order of nanoseconds timescale, so it doesn't hold for very long, if you like. But nevertheless, this triple product criteria, if you're this side of the line, you can have conditions for break even. You get more out than you put in. So this is an important thing to know about fusion. And then the other thing that gets asked quite a bit is why DT fusion? There are many fusion reactions. Why not other reactions? And this graph on this side shows a quantity reactivity. So reactivity is subtly related to cross-section of fusion, except in a tokamak, for example, we want thermonuclear fusion to take place. So you have this Maxwell-Boltzmann distribution of fuel ions in the plasma rattling around. And so folding that Maxwell-Boltzmann distribution of fuel ions, the cross-section, you get this reactivity quantity. And you can plot as a function of the plasma temperature, this reactivity quantity. And if you look at the different fusion reactions, you'll see DT in this bold line here compared against DD fusion, D helium-3, proton boron 11. It's it's significantly higher than all the others at typical plasma temperatures. So tokamaks will operate in 10 to 20 keV. So you can see it's much higher than the others. So in simply put, it's the easiest fusion reaction to do. So this is why we're pursuing it for terrestrial machines on Earth. And of course, this is very different fusion to what's happening in the sun. The sun's fusion reactions take place very, very slowly, and follow a sequence. So DT fusion, if the sun was made out of deuterium and tritium, it would just explode, and so it'd be all over very quickly. So that's fortunate. The sun's been around a long time, and will continue to be so. But fusion is happening in the sun. So fusion power plant concept. So, it's important to acknowledge and to look at who wants fusion. It's not enough to just build a fusion power plant. We need to look at the markets. We need to see, we need to look at what the cost of fusion will be, and we don't know at the moment. But of course, the most obvious route for use of the fusion reactor is electricity production. So, much like in many power plants, high-grade heat is extracted in the blanket using coolant. You boil water, drive turbines, produce electricity. So, this is a generic sort of fusion reactor. So you have a superhot plasma, DT reactions taking place. The alpha particle, at least in a tokamak, being a charged particle, will whiz around the plasma, be confined in the magnetic field, deposit its energy there. We get some alpha heating. The neutron, being uncharged, will escape the plasma, and we need that neutron to interact with a blanket, what's called a blanket, tritium breeding blanket, made out of lithium or a lithium compound. And we want the neutron to interact with the lithium. It will deposit its energy, and then we'll have a heat exchanger and so on, that feeds through to boil water to drive turbines and electricity this way. So that's a very, very simple sort of representation. But electricity is one thing, but fusion could be a very good way for generating heat for industrial processes or district heating, desalination, hydrogen production. Of course, the specific needs will vary depending on where it's deployed, but it's really important to look at those kind of factors as we're developing the technology. Now, I just want to go through briefly some of the key challenges of fusion. I've got this video here. So fusion power plant, the tokamak will be a very small part of it, with the huge amount of infrastructure that goes with the plant that is needed. So the first challenge here is confining the hot plasma at temperatures 10 times hotter than the center of the sun. So this is real footage from JET, and what you're seeing is the plasma forming and interacting with the wall, and down here is the diverter region. And now here we see a deuterium ion whizzing around inside the hot plasma, and it will hopefully meet with a tritium atom. So this is super heavy hydrogen and heavy hydrogen. It fuses, momentarily forms helium-5, which breaks up very quickly to produce helium and a neutron. Neutrons escape and interact with materials. So the second challenge is neutrons damaging the wall structure. So neutrons will cause displacements, they will cause swelling, embrittlement, they will lead to gas production in materials. And I know there's a lot of work here going on in the materials science area. So you will understand this from your simulations and your experimental work. So that's a really important area. Challenge 3 is exhausting the extreme heat fluxes. The helium ash will have to be swept out of the plasma. So there will be, this is called the diverter region, and this is where the plasma comes into contact with materials. There'll be extremely high heat loads, tens of megawatts per square meter. So managing that heat is an extremely important area, and a very hard area to look at. Challenge 4, breeding tritium and handling it. There isn't enough tritium to basically keep a fusion plant sustainable. So tritium themselves. So there's no way around it. Experimental facilities that have low fusion output, we can use tritium from fission, but for gigawatt scale machines, we'll have to breed our own. That's a big challenge. And then once the tritium's generated in the blanket, it has to be extracted, isotope separated, processed, put into pellets, and then fired back into the plasma. What we're seeing here is the fueling aspects of that. So, and then this fifth challenge, neutrons will induce activation in materials. So these will be radioactive. It won't be a good place to send humans when there are significant fusion power machines. So this is footage from JET showing the work that's been done with the mascot manipulator to remotely maintain and replace tiles inside the vessel. So the whole machine has to be thought about and designed from the perspective that it will be remotely maintained. You won't be sending humans inside a vessel of a power plant because of the radiological fields. So I'll just go a bit more into detail into tritium self-sufficiency. So, and this is a very simple kind of picture of you know, what we need to do. And there's a lot more physics on top of this. But I suppose the bottom line here is a 1 gigawatt fusion power plant will consume tritium at a rate of 56 kilograms per full power year. So, and that's a lot of tritium. And there have been estimates, you know, what is the world supply of tritium, you know, the civil applications, and estimates are around, you know, a low tens of kilograms. So you can quickly see that actually, well, you know, even if you had those 30 kilograms, you haven't got very long to operate your power plant. So this really underlines the fact you have to breed your own. So this is the DT reaction taking place. Deuterium tritium forms helium-5 that immediately breaks into the projectiles. Helium stays within the plasma. The neutron interacts. So this is the plasma, the neutron escapes, and our blanket contains lithium. And you will know that lithium has 2 stable isotopes, lithium-6, which is about 7.5% of the abundance, and the rest is lithium-7. So the majority is lithium-7. And so with this lithium-6 reaction, so the cross-section for this reaction that produces tritium happens more readily with low-energy neutrons. So neutrons interact with lithium-6, and you get another alpha particle, you get your triton, and you actually release another 4.8 MeV in this process. So you also get some energy multiplication in the tritium breeding blanket. So you get 17.6 MeV here, you get 4.8 MeV here. And then, you know, the tritium can then be extracted and put back into the blanket. Now, the problem with this really simple picture is you can see that, you know, if this was the only thing, you know, the only kind of physics that mattered, you know, every neutron would have to lead to a tritium atom, and this process would have to be 100% efficient for it to work. And of course, the neutronics is more complicated than this. In fact, there are tritium producing reactions in lithium-7 as well as lithium-6. There's the NN alpha reaction, which happens with high energy neutrons. You need to be above around 3 MeV for that to take place. And interestingly, that reaction you don't lose the neutron in the process. And there are also other things you can do in a breeding blanket, such as adding neutron multiplying materials. So materials such as beryllium has you know, relatively high N2N reaction cross section. Lead has a useful N2N cross section. Oh, it's come back again. So neutronics is really key to understanding, you know, tritium production. Can we produce enough in the breeding blanket? We talk about a quantity called TBR, the tritium breeding ratio, and if this is greater than 1, we're producing more than we're consuming in the plasma. So that's an important quantity to determine. But breeding blankets are, you know, a key technology area for the viability of fusion, and it's been great this week to see the Indian capability in this area, and you know, and the facilities that you're operating and the science that's coming out. So I'm just going to highlight some things in the international landscape, and I want to kind of emphasize that international cooperation is really key in fusion. There are many hard problems to solve, and we need to work together to solve them. And the IAEA play an important role in convening and bringing together different countries to work on these problems. And I just, you know, I'll give you a perspective here, but there's some really good publications I want to point out. the IEA have started producing a World Fusion Outlook. They started in 2023, and they've now got one that was published just last year, which is worth a read and gives you what's happening in the public and private space. And this Fusion Key Elements report, which goes into more depth on what the challenges are for fusion. So it's quite nice. And then there is this Fusion portal, FUSDIS, which allows you to look at all the fusion facilities around the world, and you can then go in and find information on whether it's a tokamak or a stellarator or an inertial fusion machine. So really worth looking at. So there have been lots of kind of exciting things happening in fusion, and that key elements report sort of goes into them, and the World Fusion Outlook. I just want to pick out two significant ones. So I say the field is heating up, and on the left-hand side here we see the result from NIF, the National Ignition Facility, and this is this approach using inertial fusion. What you see here is the hull round, this gold cylinder. It's about 1 centimeter tall here, and inside this peppercorn-sized fuel pellet, 192 lasers produces X-ray bath, and you get this implosion. So after quite a long period of time, the fusion yield from these shots was, shall we say, sort of fairly sort of mediocre, but advances in understanding the physics of this process and achieving higher compression and onset of instabilities and so on has led to really impressive fusion yields. So this result in 2023, basically they put 2 megajoules of laser energy into this hull round, and they got out about 3.88 megajoules. So the ratio of that's about 1.9. So this is a significant scientific achievement. There's a long way to go to make this a power station, and I don't think that's necessarily the NIF objective. But although it's created a lot of discussion within the ICF community about power plants from that approach. And then on the other side, at my lab, we see the world record for fusion at JET. So JET operated for 40 years, and it can operate with deuterium and tritium. And what we see here is the fusion power function of time here. So JET can operate plasmas for typically a few seconds, up to 10 seconds. And the reason that JET can only operate for short periods of time is because it uses conventional copper magnets. You put high currents through the magnets, they get hot, you have to switch them off. Of course, the pathway towards fusion power plants will be superconducting magnets, which I've seen a lot of expertise you have here at IUAC. And but JET nevertheless produced this record of 69 megajoules over a 5-second period. So it showed this sustained output over a 5-second period. So that was a pretty remarkable achievement at the end of JET's life. ITER, well, I know India knows a lot about ITER, and it's one of the main partners of ITER. The facility being built in the south of France. The objective of ITER is to produce Q equals 10, or 10 times power gain. So this is 10 times more out than is put in from the heating system. And it was great to see that fusion is supported at the top level in India, with Prime Minister Modi visiting ITER back in February this year. A picture here with Emmanuel Macron. So ITER is a really exciting thing that's happening at the moment, and it's actually been re-baselined. So the schedule of ITER has been updated by the director, Pietro Barabashi. There's an excellent paper online which outlines the reasons and the timescale for ITER. So they're looking to begin operations about 2035, moving into DT around 2039. It's the latest, and it will be a phased approach and a phased licensing approach. And ITER, many contributions from India to ITER, and I just pulled this off the ITER website, but it shows the work of Indian companies on the cryostat lid here. So this is a truly huge component, nearly 4,000 tons. And you can see, I won't read them all out, but there's lots of Indian companies that are involved in these activities, and this is just one of them. Something about private fusion, because this is also, there's quite a buzz around private fusion at the moment, and there has been so far around $7 billion US dollars invested in fusion. And this information is from a report from the Fusion Industry Association. So this is a good resource to look at what's happening in private fusion. But you can see since the 1990s, well, we have this one private fusion company. But in recent years, really the last less than 10 years, there's been this burgeoning of private fusion companies. And this is from 2023. And if you look in the 2024 report, there are even more fusion companies coming in. Yeah, I mean, some of the pictures here, this shows the general fusion, magneto-inertial approach. This is a Canadian fusion company. This is Spark in the US, Commonwealth Fusion Systems. So Commonwealth Fusion Systems have been awarded the most funding in private fusion. So they're one to watch. They're I guess, unique technology that they're developing are high field superconducting magnets, which they say will open up the pathway to smaller tokamaks, smaller machines. So maybe analogous in some ways to the path of fission small modular reactors, making them smaller could be an economic way to develop fusion. In the UK, we have tokamak energy, pursuing spherical tokamaks and also high temperature superconductors. And we have another one in the UK called First Light Fusion, which is developing inertial fusion approaches, not using lasers, but using projectile-driven fusion. So yeah, it's an exciting time. Now, I'll just get into some of the fusion neutronics. Basically, because DT fusion releases lots of neutrons, I mean, 80% of the energy from DT is released in neutrons, so largely neutron power. So it's important to know where neutrons go, how they interact, where they deposit their energy, and so on. So it's important if you're getting involved in fusion, you know, in the technology part of fusion, knowing about the neutronics is important. So you need to have capabilities to handle models and so on to look at this. So it informs critical areas of fusion power plant design. So heating, tritium breeding, activation of in-vessel components. And it provides information that inform other areas, such as material science, radiation damage, which in turn affects the lifetime of components, radiological safety, doses, radioactive waste arisings, and can help you to optimize your diagnostics. What you see in this image here in the middle is a neutronics model. So this is a model, a slice through the jet machine. So in a neutronics code, all space needs to be defined mathematically. And we use this form of geometry called combinatorial solid geometry. So all space is defined, materials are assigned to regions in the device, and then you can run this through your calculation to produce outputs like the neutron flux map here, or neutron spectra in your whichever location you're looking at, depending on how you're operating your machine. So some of the key things to enable nuclear predictions are nuclear cross-section and decay data. So the quality of this data is essential, and these need to be evaluated against experiments, differential and integral experiments, methods, the codes themselves, the radiation transport codes, and its coupling to nuclide inventory calculations is important, and these in turn need to be validated. And then models. depending on how you where you are in your design, if you're early in your design, you may want to use simple models that can be parameterized, and then as you move towards the real engineering design, you'll have to use high fidelity representations of your machine. Each of these fields is extensive in its own right, so I can only give you a skim through this. So neutronics methodologies. So there are several approaches, but there are two, broadly speaking, two main approaches for the neutron transport problem. So deterministic codes. So these solve the Boltzmann transport equation for a flux solution, and in this type of approach, your variables are discretized. So you typically have 6 or 7 variables. You have 3 spatial variables, 2 angular variables, energy, and sometimes time. So you solve the equation, and the deterministic approach will allow you to get an exact solution to your problem, but you're using an approximate representation of the physics. Whereas in a Monte Carlo approach, and in my work, we tend to use Monte Carlo-based approaches to radiation transport. So this uses continuous physics. So the cross-section data that, the neutron cross-section data can be very complex. Accelerate, we lost the connection. No. So we can use deterministic codes to accelerate the Monte Carlo code. So this can make better, better use of your computational resource. I guess one of the downsides of Monte Carlo approaches is that it's very computationally expensive. And you could say if you've got, significant high-performance computing facilities, you can throw the problem at the HPC, but some problems, even with the best HPC in the world, some problems wouldn't be tractable. And you can use deterministic to help with addressing this with using variance reduction techniques and so on. So so these are the main methodologies.
Actually, there was some technical glitch at Zoom. So you will have to share your PPT through Zoom again.
Right. Okay.
Just one minute.
Yeah, sorry.
Escape.
I really enjoyed seeing the high performance computing facilities here in Italy.
Private fusion, you said. This is the super private fusion.
Yes.
Okay. So this is superior than ITER in terms of the gain.
Private fusion. Well, there's a very broad range of private fusion companies. So I wouldn't say they're necessarily superior. I mean, maybe the narrative from the company might say that, but whether everyone would agree with that, I don't know. But of course, private fusion companies tend to be focused on the near term, I mean, there's some very, very good, very impressive private fusion companies out there, and it's a space to watch. But there are a lot of hard problems to solve in fusion, and private fusion companies aren't necessarily looking at all of them. So public sector research is looking at those. But maybe I can come back to your question later. I'll crack on with the lecture and come back to the Q&A. Thanks. So I just want to show you quickly some of the neutronics workflows that we adopt at UKAEA. So, if we're designing a early stage, fusion concept, we might start with a very simple geometric representation of the geometry and have homogenized materials and so on. A simple build. What we tend to do is we parameterize the materials, the geometry, the operations, and we can run many variants of this machine. And what we'll do is we'll feed that into a mesh-based radiation transport geometry, a model. So we have a technique this way. And then more detailed sort of machines, detailed engineering CAD. So I would say ITER is in this category. It's being built. We know what it looks like. And so we have the detailed engineering CAD. So there is a workflow where you take your CAD, you de-feature it judicially, and then you convert it into the form that the Monte Carlo code will use, if it is a Monte Carlo code. And some of the tools we use here are listed. I won't go into the details here. Once you've got your model, you can then feed it into your neutronics code. And again, I've listed 4 codes here. There are many codes. MCMP6 is very widely used, a US code developed at Los Alamos. OpenMC is a very up-and-coming, promising neutronics code. It's, as the name suggests, it's open source. Anyone can access it. We've been testing it a lot for fusion, and the capability is very, very strong. And there's some others here. And then once you run your simulations, you can, and of course, these are generally run on high-performance computing systems. Monte Carlo codes are eminently well suited to running on HPC. And then you get your nuclear analysis outputs. So, the fusion, fusion machines have very complex radiation sources. There are many to consider beside those in the plasma. It's not just neutrons being produced in the plasma. You have other sources of radiation that you may need to consider as well. You have photons as well as neutrons. You may have runaway electrons. These are plasma-based sort of radiation sources. We're using neutral beam injection to heat tokamaks and heat the plasmas in tokamaks. So you have RF-associated radiation sources that need to be considered. Neutrons induce activation in coolants. So 14 MeV neutrons can interact with water and produce nitrogen-16, which has a relatively short half-life, about 7 seconds, but it emits a high-energy gamma ray in the process. And also, you can get corrosion products into water, for example, or whatever coolant you're using. So, and those can become neutron activated. So you have this itinerant flowing radiation source that you need to be able to consider, model. And then you have other radioactive components, maintenance equipment, activated dust. There are plasma wall interactions that will produce dust. This becomes activated as well. And the work I'm showing you is there's an excellent group based in Madrid, UNED, and this paper from Rafael Juarez. So all of this I'm showing is from Rafael Juarez and his group, which is really the leading group doing ITER-related analysis in neutronics, at least in my opinion. So it's a really good capability to look at. A bit more on neutrons and activation, and I just want to play you a little video here, which just shows, gives, or at least illustrates what happens with an inventory code. So, in a fusion machine, plasma-facing wall, at least in some machines, will be tungsten or a tungsten alloy of some kind. So what happens to tungsten when you put it into a neutron environment? And what you see here is a section of the nuclide chart, Z, and neutron number this way, charge this way. And you have the 5 stable isotopes of tungsten here at T equals 0. So this is before it gets irradiated. And then on this plot, we see the elemental variation as a function of time. And if I play this, so now we're exposing this tungsten to the demo spectrum. So this is a prototype power plant, and now we're at 3 years of radiation, 4 years, 5 years. So, and you can see that at the end of 5 years, we've got a cocktail of isotopes, and you know, some of those isotopes will be stable, some will be radioactive, and other radioactive ones will have, you know, associated decay modes, gamma lines, etc. But this code, and we use a code called FISPAC to do this, and I think some Indian organisations are using this code FISPAC already, and there's a link to it here. So it's developed at UKAEA. So, you know, it allows you
Sure.
So can I take a question? Yes. The activation you have shown on several materials,
yes,
and
or tungsten, yeah.
CFC, carbon fiber composites, they have been realized very good material for plasma facing. And that kind of activation you have not.
That could be done. Yeah, that could be done. Yeah, so you know, you can define any material you want. I've just illustrated it with tungsten, but yeah, you can feed in your material composition, and you can do the same kind of simulation. So yes. So 3D activation, really important to be able to do, and that allows you to work out the 3D offline shutdown gamma dose. There's 2 papers here which go through the methodology if you're interested, and of course simulations are great, but you have to ask the question, have they been validated experimentally? And having access to a 14 MeV neutron generator, for example, is a good thing. We've done some work with an Italian group at IPA using their 14 MeV neutron generator based at Frascati to look at you know, the shutdown gamma dose rate and how simulations compare against experiment. And I noticed that IPA, you have a nice new 14 MeV facility there, so I was very impressed to see that. And again, this is work that I've been doing at JET with my Eurofusion collaborators. We took a range of ITER materials and we exposed those materials to the 14 MeV neutrons, well, all the neutrons produced in JET over quite a long period of time, more than 1 year. And we looked at comparing our simulations against experiment. So very much similar to how I showed you earlier, but we have a JET model, a neutronics model, and we run simulations with our JET operational history of neutron output. And of course, JET doesn't only operate in DT mode, it operated in DD mode and other modes. So the neutron flux varied over time. This is what you see here. So this information is fed into our MCMP plus FISPAC code to give you the time variation of, this is a copper chrome zirconium sample. What we're seeing is the isotopic production as a function of time. So this is what we're interested in. So this is the simulation part. And then we can measure the post irradiation, what the gamma spectrum is from that material. So we use HPG detectors, and this is our detector. We have a Compton suppression system that we use with this, and other collaborators in this project did the same at their lab. So we distributed the samples, measured the samples, compared calculation against experiment. And what we found was a large degree of agreement, but there were some notable discrepancies, and we're still looking at the explanation for these discrepancies. And there's a paper from myself and several co-authors that go into more detail into this. But one of the things that we're investigating is, how reliable were the materials certificates defining the elements, and that's one possibility. And there is some surface contamination from sample preparation techniques that may be at play here. And actually, one thing that actually links to AMS here is we started an interaction with the University of Vienna, who are exploring. This is what we measured. These are the nuclides that we measured using gamma spectrometry, but accelerator-based mass spectrometry could be a really attractive technique to use for those difficult to measure nuclides that don't make sense to measure using radiometric techniques. So nuclides such as niobium-94, which is extremely long-lived, it's something like 20,000 year half-life. Of course, in fusion, we want to avoid anything that has a long half-life in production, but the ability to measure those difficult to measure nuclides would be really good. So I've learned a lot about AMS from this morning, and I appreciate that. I've got a long way to go, but I'm interested in other techniques that might be useful to take this work a bit further. And we're interested in neutron facilities, and I'm just listing some of the facilities that we've used. Some in the UK, we've got a 14 MeV facility at ASP. Here's the Frascati neutron generator. We've used facilities in the Czech Republic, University of Birmingham, and so on. So being able to validate simulations is really important. Just another application. So we're getting involved in, with supporting private fusion. If you're serious about fusion, you need to know about the neutronics. And I suppose, private fusion companies, they don't necessarily have all the capabilities that are needed at the beginning. And it made sense for us to work with Gaus Fusion. So this is a company based in Germany, in Garching, I believe, and their mission is to construct a gigawatt class demo fusion power plant based on the stellarator concept before 2045. So our neutronics work, so because of the complex shape of stellarator coils, and you see these complex coils here, it required a different approach to neutronics modeling. So we really leveraged some excellent work from the University of Wisconsin, Colin Moreno, who developed this parastell parametric modeling for stellarators, and we adapted it with some other tools in order to produce a mesh-based stellarator model. And that's the point at which you can then pass it through a neutronics calculation and simulate all the things that we're interested in. So, and then from that, you can produce, you can calculate tritium production, all the things you want. So nuclear heating, what is the, fast neutron flux to superconducting coils, and do that in a stellarator. I'm just going to finish with a few UK developments, and then I'll turn it around. So the UK fusion strategy. So our previous government published this report in 2023 towards fusion energy 2023. So now we have a Labour government who are in the process of updating this strategy. But the strategy as it stands is for the UK to demonstrate the commercial viability of fusion by building a prototype fusion power plant in the UK that puts energy onto the grid. And so we have this quite extensive program that's begun now. And then the second strand is for the UK to build a world-leading fusion industry, which can export fusion technology around the world in subsequent decades. So those are the kind of main sort of features of this strategy. And we have this Fusion Futures program to foster the innovation and stimulate. An important aspect is stimulating the industrial capacity to develop fusion. And some of that funding is to enhance international collaboration. And the most recent announcement, actually, which was just earlier this month, there's a British Fusion Investment Fund called StarMaker One, which is seeking to kind of stimulate private industry. So we're trying to sort of kickstart it. Well, it's already started, but we're trying to kind of accelerate it even further. Now, in the UK, we have a program called STEP. So this is now run under an organization called UK Industrial Fusion Solutions in UKAEA. So this was kind of separated out of UKAEA, and it's designing the concept for STEP at the moment. And this is some work from my colleague Tim Eade. But you can see the basic parameters of the machine as it is at the moment in this design point. So it has a major radius of 3.6 meters. It's a spherical tokamak, so it has a low aspect ratio compared to conventional tokamaks, 1.8, and some other parameters here. The fusion power aiming for 1.6 to 1.8 gigawatts, and of course producing net electric power, a small amount of electric power, 100 to 200 megawatt electrical, but it's a demonstration machine. It's not. This isn't a commercial machine. And some details here on the magnets. So there's a lot more detail in these Royal Society papers. So if you're interested in STEP, I encourage you to have a look at these publications. There are several here. This is my penultimate slide now, but I want to mention a new tritium breeding program called Liberties, which was 200 million investment into this area. And the idea here is to basically have a neutron source, and around that neutron source, the ability to bring in, companies, tritium breeding blankets, it could be consortia. So bringing in their concepts and irradiating them in a real fusion neutron environment, and get some understanding of what's the tritium production rate, what's the efficiency of extraction and processing. So this is a really important area of the fusion. And I won't read out the companies, but we're engaging with several commercial organizations and universities as well on this. So my concluding remarks, really, fusion energy offers a promising low carbon energy source for the future, but at the same time, it's one of the greatest challenges at the moment. So there's been a lot of recent scientific achievements of late. So I've mentioned NIF, and I mentioned the JET results, and there's been global interest in this and a commitment to advancing fusion technologies. And there's been quite a lot going on in the private landscape as well. So that's sort of notable. And in the UK, we have a fusion strategy, which I just went through, but there's several other ambitious domestic programs from member states around the world. Fusion's a neutron-rich energy source, so having a capability in neutronics is really important. And the capability needs that you need are, methods and nuclear data. You need the experimental facilities, diagnostics. And I think most of all, you need highly skilled and dedicated people. And that's not just neutronics. You need that in any kind of scientific endeavor. And international collaboration at this stage of fusion development is needed to address these challenges. So with that, I will turn it around. And if you'd like to ask me any questions, please do. So thank you very much.
Yep. Thank you, and any question?
This reactivity plot that you showed, fusion of different, it is based on some model or is it empirical?
The plot. It's based on it's simply based on a Maxwell-Boltzmann distribution of fuel ions.
But Maxwell based we only give the velocity distributions. The reactivity, the cross section comes from where?
That comes from experimental measurement. So that's
So it's empirically.
And of course, I guess not every single energy will have been measured. So there will be an evaluation of the cross section. So that these are relatively well known. The cross sections are relatively well known. Of course, there are cross sections that aren't as well known, but I think these fusion cross sections that I'm showing here are well known.
Particularly at low energy, it's very difficult.
At low energy, yes, that's true. Yeah, and of course, the knowledge on cross sections has been derived from accelerator science. So this has been a key contributor to this information. So it's basically a folding of the cross section with the Maxwell-Boltzmann distribution. So it's of course this is still simplistic because plasmas can behave. They're not, they may have a component of Maxwell-Boltzmann distributed fuel lines, but we're also heating up plasmas using neutral beams. So we're firing energetic particles into plasmas as well. So they're not, we know to get net energy out, it's thermonuclear fusion that will be the way to do this, because you can't get net energy out of a beam-driven system. This, a lot of the energy is lost through Coulomb scattering interactions, and only a few fusion reactions will take place. So you have to raise the average energy of the whole system to these temperatures of 10, 20 kV for this process to take place. Thanks for the question.
And for this blanket, for the breeding blanket,
yes,
use lithium only, or is it? Some other materials are also tried.
So lithium is needed. It could be a lithium compound. So some of the main candidates, it's not only lithium metal, but actually some of the main contenders for tritium breeding blanket will be lithium ceramics, so like lithium orthosilicate or lithium titanate.
And what is the optimum energy of the neutron? Because the neutrons are 14 MeV.
That's right. Well, So this depends on the particular choice of tritium breeding blanket concept. So the Indian tritium breeding concept that's, I think, being pursued for the ITER TBM program. There's a lithium titanate breeder concept, but there's also an exploration of lithium lead metal coolant as well, tritium breeding in coolant. So there are these, solid type and liquid metal breeder concepts. The optimum energy. So 14 MeV neutrons are quite helpful for tritium breeding because you have a reaction with the lithium-7 isotope. So if the energy is above around 3 MeV, you can produce tritium hydrogen neutrons. So that's good. Is there an optimum energy? If you only had lithium-6 in the blanket, then you just want low energy neutrons. You want them to be as low as possible. But in fusion, you also want to increase the population of neutrons in your blanket. So high energy neutrons are also very good at inducing neutron multiplying reactions. So end-to-end reactions in beryllium or in lead, quite useful. And again, there are energy thresholds for these reactions. So this is important. What we do is we run the neutronics simulation. So you can get some kind of idea from looking at the cross sections, the relevant cross sections, but really you feed in your system into a neutronics code, and then you basically work out.
So the neutronics code are what the 4 you showed, 4 or 5.
Yeah. So MCMP is very widely used, and it's perhaps the most well-validated code around in the fusion community, but OpenMC is very, very good as well. So there are numbers, and some have used Géant. It's not very widely used in fusion. It's more that's usually more used for, high energy physics type simulations. Yeah, this is the way to calculate it. Yeah, it depends. And the other parameter besides which material and what neutron energy you need is the lithium-6 enrichment as well. So if you go towards a lithium-lead blanket concept, then you get your highest tritium breeding ratio from a very high enrichment in lithium-6, 90% enrichment, whereas with a ceramic breeder, you can have lower lithium-6 enrichment. And enriching lithium-6 is quite expensive, so there may be some economic benefit from using lower lithium-6 enrichment. But yeah, the neutronics will inform what the best choice of blanket is. And of course, you've got between your blanket and the plasma, you have your first wall material. So, and this also affects your efficiency of the use of your neutrons. So you want to keep your first wall ideally neutronically thin to maximize your tritium breeding ratio. But there are technological reasons why it can't be so thin, and you need to obviously protect other components from the plasma and so on. So there's many factors to consider in this, but yeah, tritium breeding is such an important area for fusion. We need to get it right.
And any projection that how the contribution of this fusion energy is going to be more, but from energy generation point of view?
Yeah, well, I hope so. There's still many issues to resolve. We are still very much in the experimental phases of fusion. We haven't really gotten into with tokamaks, we haven't got to the stage where we're producing more energy out than we're consuming. So, but ITER is the main machine that will demonstrate that, unless a private fusion company comes along sooner to demonstrate that. And this will be 2035. ITER will begin operations, then 2039 when it does DT operations. So it's going to be around that period where we move into the phase where actually we've proven that we can produce more energy than we put in. But and ITER will test many of the technological aspects that are needed for fusion power plants. But you will need a demonstration machine beyond that. So what ITER won't do is it won't produce all of the tritium that it consumes. You will test some tritium breeding blankets in modules, but a fusion power plant will have to have a high coverage of lithium blanket, a high solid angle in order to breed enough tritium. So demo machines are foreseen to do that. And in the UK, we've got the STEP machine, and that's expected to be operational in the 2040s. And different countries have different timescales, and you can say so. Once if you do that in the 2040s or 2050s, and that's successful, you've then got the commercialization, I suppose. So I guess I'm going into this is my opinion. If you ask people in private fusion, they might say, no, we can do this much sooner. We can have a commercial machine by the middle of the 2030s. But I expect that we won't see fusion power plants in the commercial phases of fusion until the second half of the century. And then the actual market penetration will take some decades to ramp up. So even if we've got a commercial machine 2050, it will take longer to just build the machines, I suppose. And there's also the supply chain. Developing the supply chain is important too.
That's why I asked, because World Energy Agency are advising to explore more of the non-renewable energy.
Yeah.
Component.
Yeah. One of the things that's come up is if we need enriched lithium-6 in a breeding blanket, and a breeding blanket might need, ton scale or 10-ton scale of enriched lithium-6. Where are we going to get the lithium-6 from? And just scaling up that enrichment capability will take some time. So, and if anyone that's pursuing DT fusion needs enriched lithium-6, you know, that's a kind of time limiting factor, I suppose. But that's just one example, I think, the supply chain. But that's why having an industrial strategy to grow the supply chains is important. Okay.
You had shown one conceptual diagram of this entire process of fusion energy, right? I think the next slide.
This one, yeah.
So, yeah, as you were saying that we are still in the experimental phase, but the remaining part, is that established technology, or that also has to be fine-tuned?
Yeah, well, yeah. That, I mean, that's what needs to be developed, and that is being developed as well. And I've seen here in India that there's some excellent technology facilities, like a liquid metal testing loop, ceramic breeder testing loops. I mean, I think the breeding blanket is one of the key pieces of technologies. The materials, knowing how materials will behave in high energy, high flux neutron environments is another.
I'm asking, even when the energy is produced to supply it to the grid, that part also, is that
I would say that part is much better. That's mature. I mean, you know, if it's say, let's say a water cooled system, that's conventional technology. We know how to extract heat and utilize that. So the bigger challenge, I think the bigger challenges are the plasma, the turbulences, controlling turbulences in the plasma facing materials, which see the highest neutron fluxes. We know how materials behave in fission environments, which also produce neutrons. That's useful, but fusion neutrons are different. So there is some discussion around the testing facilities for materials, you know, and there's a facility being built in Granada called IFMIF Donez, which is actually an accelerator. It's a 40 MeV deuteron being 125 milliamps onto a flowing lithium target, which will produce lots of neutrons, high energy neutrons. So it's more relevant to a fusion environment. And there's other discussions going on around neutron sources needed to test fusion. So there's a lot, you know, there's a lot left to do, I would say. Yes, okay, thank you.
Yeah.
Last question. If we review the progress of the ion development, then developing negative ions of hydrogen or deuterium, we see that we have even not reached to the milliampere of the brand. But for ITER, this NBI development, we need 40 ampere of the current. That rating for the successful. So how do we see this? Can the answers be really relied for that kind of rating?
Yeah, I mean, yeah, MBIs are one of the key ways to heat plasma. We used MBIs extensively in JET, and ITER will use MBIs. I mean, there is, you know, there's other ways to heat plasma too, and you know, electron cyclotron resonance heating and ICRH as well, the techniques, and of course the, you know, passing current through the plasma is the third way to heat it. I think a lot are considering the use of MBIs, but there may be, it's straying out of my area of expertise, but I have lots of ion MBI experts at Cullen who could answer this. But I mean, at STEP, we're not necessarily, you know, going to be using this type of heating system. I mean, I guess one of the problems with using NBIs is you need a big aperture into the machine in order to supply the, you know, the energetic particles to heat the plasma. But that aperture is also a pathway for neutrons to escape, and it's also taking up space to breed tritium. I mean, you have to keep you absolutely have to keep the plasma hot in order for fusion reactions to happen. But from a power plant concept, if you can use other forms of heating that would be quite attractive, I would say, because any aperture into your plasma will cause neutron streaming downline, and that will cause you some radiological problems. But ITER's using MBIs, and because that's a tried and tested route to achieving these hot plasmas.
Calculation for this CR or high frequency heating everything. The temperature which is recommended, that this kind of temperature has to be there. That is not possible by only HF heating, high frequency heating, or ECR heating like that. That is why this NBI is also needed. And the rating that is used for as far as the iron source height is concerned, that current rating is used. Otherwise, that kind of temperature which is expected, that this temperature has to be there. It looks difficult.
Well, I mean, that there are some alternative possibilities for heating, but I think many of the sort of players in the field are exploring, MBIs for their systems at the moment. But I mean, there's some problems there. I suppose with going towards better confinement conditions, with high fields, with ITER machines, you having a better confined plasma will, and having alpha heating, because that's where we want to get to. We want the alpha heating from the DT reaction to be contributing to the heating of the plasma. That's how you achieve kind of high Q values that are needed for power plants. So less reliance on that external heating is where it needs to go. But I guess watch the space from the various players in the field. I'd say. Thanks.
Yeah, thank you for a nice lecture.
Thanks. No, thanks for coming along. Appreciate it.
Any other question? Yeah, please.
In JET, you use copper magnet for confinement of plasma, right?
That's right.
How much field do you use?
The field is 5.2 Teslas. Let me. I don't know. Is it down to 3 Teslas?
3.2 somewhere.
3.2. Sorry, I think I was quoting ITER's field. So 3.2 Teslas.
The magnet must be heavier and bigger in size, right?
Yeah, they're very substantial. I don't know the maths, but I don't know if there's some picture. If you go to our website, you can see the size of those coils. They're very substantial. Yes. Yeah. Yes. Okay. Thank you.
So just one question. So inside this, there is a hostile environment. Of course, the temperature is very high.
Yes.
What is the life of the things which are there inside? As you said that a lot of tungsten hit isotopes.
Yeah. So the lifetime. Well, this is an extremely important consideration for the commercialization of fusion, of course. I mean, in the existing experimental machines like JET, we've actually replaced the tiles quite frequently over its lifetime. And actually, there are pictures of the machine, how it's changed since it was first created in 1983. And, we didn't have a diverter in 1983, and then that came in later. And then the tiles at one point were carbon plasma facing tiles. And then these were replaced with what was called at the time the ITER-like wall, which are a combination of tungsten and beryllium facing tiles. And studies on plasma wall interactions and erosion and dust production in plasmas have been done. I mean, because JET, although it's produced world record fusion, it's the neutron environment is much smaller than what we will expect in a fusion power plant, which will, be producing, like 6 orders of magnitude higher neutron fluences, even more than that. So there's a long way to go with the nuclear aspects of fusion, I would say. But yeah, there are many other tokamaks around the world which have explored, plasma wall interactions. Machines in Germany, for example, have looked at this. So there's it's definitely an international collaborative effort in trying to understand these kinds of effects. And no doubt there'll be more learned from ITER once it begins operation, because ITER will operate with 500 megawatts of fusion power in its final phase of operation, and this is significantly more than any other machines produced before. So the maintenance and replacement lifetime is going to be important. Important questions to know.
So that we thank Professor Packer.
Thank you.
And may request the director to say a few words, and then
I just
Yes.
and we are thankful to Sir Director to allow this lecture to take place. This is a small memento.
Thank you. Thank you. Yeah, thank you. Yeah, I really enjoyed coming to your organisation. It's been excellent. I've thoroughly enjoyed the discussions, and it's been amazing to see what India can offer. Really, so I'm much appreciated. This will go on my mantelpiece when I.
This is actually IUSC, no?
Yeah.
This is the tower. Electron tower.
I got the view from my room. Yeah, so it's thank you. That's really.
So you had gone up to the top floor of.
Yeah, I've been clearing out. That's a nice memory. Yeah, so thank you. Right. So much appreciated. Thanks a lot for coming.
Thank you.
Thanks.
Thank you, everyone. Thank you, sir. Abhi, the name. Yeah, you can keep it.
Oh, thank you.
You can ask him to close it. Maybe you can switch off the YouTube live. Maybe he's conducting accident. Maybe I will switch off from here. If we log out, then everything will switch off. Log out from new sign.
वो नीचे ही है बेटा सबसे हाँ
Leave.